So yes, I am Frederic from ECMWF. First of all, thank you for the invitation. It's a pleasure for me to be here today. So I will give a presentation on the sub-seasonal to seasonal prediction project with a specific focus on the prediction of extreme events. So in this talk, I will first have an introduction, a brief introduction about the project itself. Then I will talk a bit about S2S predictability, and then the S2S database, which is one of the major outcomes of this project. And in the second part, I will talk about the S2S prediction of extreme events using the S2S database, and to discuss then the current limitation in S2S prediction, and then I will go to the conclusions. So first of all, the WWRP and WCRP S2S project. Very briefly, this project is a WMO project, which started in the end of 2013. Originally, this project was scheduled to last 5 years, but at the end of 2018, we got a second phase, an extension of 5 years, which is referred to as S2S Phase 2, which covers the period 2019-2023. So we are quite close to the end now, one more year to go. We have an international coordination office hosted by APCC in Korea. We have also a trust fund with contributions from several countries like Australia, Canada, UK, and Germany. So this project focuses on the time range, which is the S2S time range, which corresponds to the time range between 2 weeks, or more than 2 weeks, but less than a season. Sometimes S2S is referred to as a sub-seasonal to multi-year, but in this case, S2S is really slightly less than seasonal. And because this time range fills the gap between weather and the climate, this project is under 2 programs, the World Weather Research Program, WRP and WMO, and the World Climate Research Program. So I don't want to bore you much with the programmatic itself, but just one slide to mention a bit the structure of the project during the first phase. During the first phase, the project was organized around 6 thematics. One was the interconnections, Madden Oscillation, monsoons, Africa, and one on extremes, and one on verification products. And then we had several cross-cutting activities. But the main outcome during the first phase was to set up a database which contains operational forecast to provide to the research community. The second phase of the S2S is organized differently. The S2S database is still at the heart of the project, but then the main topics became a sort of a cross-cutting activities, and some of the cross-cutting activities became main sub-projects like land, ocean, stratosphere, aerosol, MGO, technician, and ensembles. And the extremes became cross-cutting activity in this second phase. Okay, so I will go now to the second part, which is on sub-seasonal to seasonal predictability. So as I mentioned earlier, so S2S will cover the time range between 2 weeks, but less than 3 months. And so it's a time range that fills the gap between weather and seasonal forecasting. So weather forecasting is essentially an initial value problem. So that's mostly predictability of the first kind. While seasonal forecasting is justified by the fact that the atmosphere boundary conditions evolve very slowly, like SST, sea ice, snow cover, soil moisture. And we can predict those boundary conditions more than a month in advance. We can predict SST anomalies sometime more than 6 months in advance, which can tell us something about the climate in 6 months. So S2S is a bit a difficult time range because it's a time range which is a bit too long for the atmosphere to still have a memory of its initial conditions, so a bit too short for the boundary condition to evolve beyond, to provide predictability beyond simple persistence. But usually we consider S2S to be a sort of a mixed this combination of both is a mixed initial value problem, for example, the MGO, and boundary problem with soil moisture, snow cover, and SST. So at the weather time scale, the products are usually issued, we issue forecasts on a daily basis or sub-daily basis. For the longer range beyond 10 days, we cannot predict the variability from day to day. So usually the predictability is more over a long time range, time averaging. For seasonal, usually the products are on a monthly or seasonal time, or based on monthly or seasonal averages. For the S2S time range, usually they are based on weekly averages or bi-weekly averages, sometimes pentats. But as I say, there's usually very little predictability from day to day. So the main source of predictability at this time range, so they include the Madden Oscillation, the thermometer, stratospheric initial conditions. We have Rossby wave, SSTCIs, maybe aerosols. And probably arguably the most important one is Madden Oscillation, which is characterized by a convection taking place in the Indian Ocean and then moving slowly eastward towards the central, towards the central Pacific, the west and central Pacific. And is followed by dry conditions. So usually the MGO is classified under 8 phases. Phase 2, 3 correspond to the active phase of the MGO over the Indian Ocean. Phase 4, 5 corresponds to the MGO over the Indian Ocean, over the maritime continents. 6, 7 over the West Pacific. 8, 1 is opposite of phase 4 and 5 with dry conditions over the maritime continent. So the MGO was discovered in the 1970s, but it took quite some time to understand the importance of this event, of this phenomenon. It was found that, of course, the MGO has a large impact over the area where it propagates. So most of the tropics is affected strongly by the MGO. The MGO has also an impact on the Asian monsoon, Australian monsoon. And it has also an impact on the extratropics through the propagation of Rossby waves. And it was found, for example, that the MGO has an impact on the NEO, on the European weather regimes frequency. So it has also a large impact on extreme events. It has an impact on tropical cyclones. It can have an impact on floodings over California, over South America. And it has also can have an impact on the wind anomalies over Europe. If we do a composite of phase 4 of the wind anomalies during phase 4 over Europe, we can find very, very strong anomalies over north of Europe. And during the opposite phase of the MGO, we get weaker winds over the northwest of Europe. A second source of important source of predictability, particularly for the northern hemisphere, is a weak stratospheric vortex events. Those events are less frequent than the MGO, which we can have several MGO per year. But in terms for the weak vortex event, we usually get on average about 1 per year maximum. And so it's characterized by a weakening of the polar vortex above the North Pole, or which the vortex can be either displaced or split into. And this is characterized then by a change in the stratospheric wind, an inversion of the direction of the stratospheric winds, and can also lead to a warming in the stratosphere by 30 to 40 degrees, which is Celsius, which is enormous. So this impact has been found to, in the stratosphere, has been found to propagate in the lower troposphere. And the right panel here shows a composite of 2-meter temperature anomalies during the 30 days following weak vortex, stratospheric vortex events. So this is characterized by cold conditions over West Europe and North Europe, and warm, significantly warmer conditions over Southeast Europe and part of Asia. So one mid challenge in the S2S prediction is the fact that the forecast scale is not constant in time. I mean, for medium range, short medium range forecast, we expect to have a good scale, a good prediction for tomorrow weather almost every day. There's sometimes some forecast burst, but it's relatively rare. But as a S2S prediction, as a S2S time scale, the scale is much, much more variable. And it depends strongly on the occurrences of some of those sources of predictability, which can be referenced to as windows of opportunity for forecast scale sometimes. So, for example, if we have a strong MGO or weak vortex events, then we can expect more predictability in the following months than normal. And this is illustrated by this, figure from a paper by Domez and al. In 2019, where they looked at the predictive skill of 1,000 hectopascal geopotential height in several S2S models in normal conditions. So if we average all the cases, as you can see, the anomaly correlation is fairly low. So that means that on average, the forecast scale at week 3, sorry, that for forecast for week 3 is generally relatively modest. However, if we take only the cases where we have a weak stratospheric vortex event in the initial conditions, then we can get much higher anomaly correlations there. So suggesting a much stronger scale following the weak vortex event. And we find similar results if we consider the strong vortex conditions. So for the MGO, it's we also found that if we look at the forecast scale over Europe following an MGO, strong MGO in the initial conditions, usually lead to a much more reliable and skillful forecast over the Northern Hemisphere. A second big challenge that was found more in the more recent years. I mean, over the last 20 years, there's been a lot of progress to understand the predictability as this time range and to identify various sources of predictability, the individual source of predictability. So I think there is a good understanding now on how each source of predictability affects the S2S forecast scale. What was found more recently is that actually the source of predictability interact between each other. There's been a lot of excitement a few years ago about the link between QBO and MGO. It was found that during the easterly phase of the QBO, the MGO is significantly stronger than when we have a westerly phase of the QBO. Then we have MGO, and the MGO can be found also to be a precursor, sometimes on stratospheric sudden warming events. MGO, NAO there's been a very strong relationship. So we know that following an MGO, an active phase of the MGO in the Indian Ocean tends to be followed 10 to 15 days later by a positive NAO, and vice versa after a phase MGO in phase 6-7. Interestingly, it was found recently by Heiding too that the NAO plus can be a precursor for the genesis of an MGO. So there seems to be a two-way interaction between the MGO and the NAO. MGO and ZO is also, but the source of predictability at the S2S time scale also seem to interact also with source of predictability at a longer time scale, like for example the MGO and ZO. It was found in the 1990s that the MGO through the occurrence of westerly wind bursts can help intensify on the El Niño events, like in the 1997 case. But ENSO El Niño also modulates the MGO. ENSO also modulates the MGO. So here again, it's a two-way interaction. And then we have, it was found also recently that ENSO has an impact on the MGO teleconnections. This is for a recent paper by Lee et al. In 2019, where they look at the frequency of weather, the four European, Euro-Atlantic weather regimes following an MGO in phase 1 to phase 8. So this is similar to the figure to the Cassou 2008 paper. On the finding that following an MGO in phase 2-3 tends to be followed by an increased probability of an NAO plus, occurrence of NAO plus, and we get the opposite following an MGO in phase 6-7. But then they did the same figures, but considering only the El Niño years and La Niña years. And they found that during El Niño years, those teleconnections are clearly amplified, while they are much more reduced during La Niña years. One possible argument for that is the impact of El Niño of ENSO on the Pacific subtropical jet, which is retracted much to the west during La Niña phase, making it more difficult for the Rossby wave to propagate from the Indian Ocean to the Atlantic. And then if ENSO has an impact, it's likely that decadal variability like the PDO also must have an impact also on those teleconnections. And global warming also has been found also to have an impact on those teleconnections. There's been a recent paper showing that the MGO teleconnections will be quite different in future climate. So the main question now is do we have a full understanding of all those interactions? Is there some others we do not know? Another important question is how do model current operational systems, state-of-the-art model represent the source of predictability? Or do they represent the impacts on those sources of predictability? And how do they also represent the interactions between those various sources of predictability? So to try to answer those questions was the main motivation for the establishment of this database, that the WCRP S2S database. So this database contains daily real-time forecast since January 2015. It opened about 7 years ago, and also reforecast from 12 models, so from 12 operational centers. 2 models will be added soon. One is from IIT MIMD in India and one from NASA. So the forecasts are not in real time. They are required in real time, but we have an embargo of 3 weeks. The main reason of this embargo is for data policy reason, because for many centers, those forecasts are commercial products. The forecasts are all archived with the same grid, with a 1.5-degree grid, with the same format grid 2, although there is an HCDF converter available. About 80 variables are available. They include 3D variables and 10 pressure levels. And recently, we added a few ocean subsurface. We added about 10 ocean subsurface variables on sea ice thickness as well, which allow also to look at the S2S predictions, also and to look at ocean processes. So the database is hosted at ECMWF, CMA, and IRI, and you have more details in www.s2sprediction.net. So the models in this database, so we currently, so as I said, we have 12 models, although one of them was from BOM has been stopped a couple of years ago. It was a POAMA model, which has been discontinued, and work is ongoing to implement the new model Access 2. And this year we got a new model for IAPCS from the Chinese Academy of Science. So the resolution of those forecasts extend between 32 days to 60 days. The resolution is quite variable, between 200 kilometers for the coarsest one, to 35 kilometers for the finest resolution one. And they are run, there's 2 different strategies for running them. Some centers run them very frequently, several times a day, with a small ensemble size. For example, 4 ensemble members, and usually the forecasts are produced in live mode. You combine the latest forecast with the forecast produced over the past few days to get a sufficiently large ensemble. Or they are produced in a burst mode, like at ECMWF, where we run the forecast twice a week, every Monday and Thursday, with a very large ensemble size, 51 members. And then we also provide archiving, the ANCAS, which are used to calibrate those real-time forecasts, and which are also used for skill assessment. And those forecasts are sometimes fixed. They are produced once for all. That's when the system lasts a very long time, like, for example, CSS version 2. Or on the fly, like ECMWF, when we change model physics very frequently, almost once a year. There's very large differences in the reforecast length. Some centers archive just 12 years, produce just 12 years of reforecast, some others 40 years. And the frequency is very different between models. Some are produced on daily basis, some weekly basis, some monthly basis. And so there's quite a lot of variety, which makes it difficult actually to look at multimodal ensemble with the ANCAS. However, one achievement, I would say, of the S2S project was to harmonize the real-time forecast. At least now, all the centers are producing a real-time forecast every Thursday. So some of those models are coming from the seasonal forecast community. So they are usually fully coupled. Some other models are more an extension of medium range forecast. So the majority of models are coupled with the sea ice components, but a few of them, at least 3 of them, are uncoupled. On just a few numbers before, just to mention that currently the database has 200 terabytes. We have served more than 2,000 users from 91 countries, and there's been so far more than 270 publications on the database. Okay, so now I go to the second part of this talk, which is a prediction of extreme events. So before starting, I just want to mention that there's 2 types of, here we consider 2 types of extreme events. The first one are I would say, the most obvious one for this time scale. So they are the large-scale, long-lasting events, which last typically more than a week, like heat, cold wave, drought, large floodings. So that's the type of events we expect S2S to be model to be able to predict. So that's more an initial condition problem. So here we try to predict the onset of those events, the time evolution, and the decay. And then we have a second category of extreme events, which are small-scale events. Those we don't expect to be able to predict individually at a long lead time. like tropical cyclones. We don't expect to be able to predict that Katrina will hit New Orleans 3 weeks in advance. We have flash floods, tornadoes. So here we don't try to predict individual events, but we try to predict the statistics of those events and changes in the statistics from 1 week to another. The main reason for that is that we expect here the predictability here to come from the large-scale conditions. Those events can be modulated by large-scale conditions like MGO, sometimes ENSO, SSW, SSTs. So I will go through a few examples of each. First one is a prediction predicting extreme events. So here we look at the prediction, for example, of the prediction of heat waves. So the first example here is the Russian heat wave, which occurred in July-August 2010. At that time, it was the worst heat wave on record over the past 33 years. So it was more for 55,000 days. It was a wide range of wildfire smoke. And this plot shows 2-meter temperature anomalies from ERA interim for the week of 1 to 7 August 2010, which was the strongest, which was the worst week of this heat wave. So we can see that the heat wave extended quite over a large portion of East Europe and Russia, with a maximum of, with a temperature anomaly exceeding 8 degrees C, which is enormous for a weekly mean. So in terms of a time evolution of this heat wave, here the black line represents the evolution of the heat wave in ERA interim from week 1 to week 10, week 1 being the middle of June. And the y-axis represents the 2-meter temperature anomalies. So the yellow represents the 5 percentile in the climatology of ERA interim, and the gray represents the 1 percentile. So we see that the heat wave started with warm anomalies, but nothing exceptional. And then by mid of July, started to go to the 1.5 percentile. And then the maximum went in the first week of August, where we were way within the 1 percentile. And then it stopped around mid-August. The blue line represents the time evolution in week 1 of the ECMWF reforecast, showing that the model represented fairly well this time evolution. It overdid a little bit the amplitude of this heat wave, so a week in advance, but overall it was a fairly good forecast. For week 2, which is in green, and week 3, which is in red, the onset of this heat wave seems to be displaced by about a week, and the decay also by a week. But the timing is overall relatively, or the maximum is overall relatively well predicted in both cases. So if we focus now on the week of 1 to 7 August, and we look at the 2-meter temperature anomalies over the box I showed previously, this shows the forecast at different, from ECMWF at different lead times. So this is from the reforecast. So we have 11 member ensemble, and each circle represents one ensemble member. We can see that forecast at day, the red represents the observed value. So forecast at day 1 to 7 predicted relatively overdid a bit over predicted a bit this heat wave. And of course, as we go for longer lead time, the ensemble mean, which is in the black dot, goes more toward climatology. But for week 3, we can see that the ensemble mean is still way within the 5%, close to 1 percentile, and more than half of the ensemble member predicted 2-meter temperature anomaly within the 1 percentile. So although none of them reached the observation. So although at this time range the model didn't predict the true amplitude of this heat wave, this forecast at this time range should have been useful, actually, as an early warning, because at least 50% of ensemble member really predicted something quite exceptional would happen at this time range. If we go further in lead time, week 4, the model tended to predict warm anomalies, but to the order of 1 degree, so nothing exceptional. And not many ensemble members go into the really extremes. Another example of a heat wave is a more recent one, is the North American heat wave of June 2021. And the ability of the S2S models to predict this heat wave was assessed in a paper by Lin et al. In GIL and Mo et al. In Nature Communication very recently. And in those papers, so the authors looked at the average 2-meter temperature over this box. On the bottom panel represents the prediction of 2-meter temperature anomalies in various S2S models, which is the x-axis. And the observed value is a line here. So this shows that this heat wave was relatively well predicted at week 1. But week 2, week 3, the model failed to predict. They predicted a slight warm anomalies, but nothing like a severe event, nothing like an extreme event. So there's also, for this specific case, there seems to have been some predictability within the first 10 days, but not really beyond. On the middle panel represents the average, so that 500 anomalies in the ECMWF forecast. So in the paper, they try to evaluate what was the cause of the processes that were responsible for this heat wave. And it was found that actually, if we look at the Z500 patterns, they are typical of, they are almost a canonical response to a boreal summer intraseasonal oscillation, which is this northward propagation of the MGO in summer, which was in phase 7, so which active convections over the Philippines. And so this is quite a typical response to this BSISO. But a second very important ingredient was atmospheric river, which also originates from the Southeast Pacific and reach the coast of the north of North America just before this heat wave, so bringing a lot of high moisture conditions, which was quite important to create this heat dome. And the right panel shows the model predicted relatively well this BSISO. They represented fairly well those tail connections, but they failed to represent properly this atmospheric river reaching the Pacific. They predicted it relatively well up to North America, but the top panel is in era 5, so we see that the moisture go within the land, while in the models, precipitation stopped at the coast. So which could be quite one ingredient, one reason why the model failed to predict this event more than 10 days in advance. So the ability of S2S model to predict heat wave was also assessed in a recent paper by Domesian et al. In 2022. This paper, the authors looked at the several different heat waves, which are listed on the left panel in era 5, over different regions, one over northwest, over west US, one over northeast Europe, one over southeast US, and one over China. And the right panel represents the prediction at week 3 of this event, showing that for some cases, the model did a fairly good job actually at predicting those events 3 weeks in advance. In other cases, however, the forecast cases, the model was not as successful. Okay, so those sources we events over Europe are often linked to the prediction of Euro-Atlantic weather regimes. For example, a negative NEO in winter can be conducive to cold conditions, like during the very cold winter 2009-2010. And so the ability of the S2S model to predict weather regimes is quite an important ingredient for the ability of those S2S model to predict those blockings or those heat waves or cool waves in winter. So Frederic et al. 2018 looked at the predictive skill of the different S2S models for NEO plus, NEO minus, blocking Atlantic ridge. And they found that actually the model has some skill to predict NEO plus, NEO minus up to about 3 weeks, but the ability of the model to predict blocking on Atlantic ridge doesn't exceed 2 weeks. Those are much less skills than to predict those two weather regimes. So I presented a few examples of heat waves. Now the question is, what is the general skill of the model to predict those extreme heat, weekly mean anomalies? And for that, one possibility is to look at decile, to look at decile probability. And this is an example from the ECMWF model, looking at the probability of 2-meter temperature to be in the upper decile. The verification, here we look at the Roth verification. So the perfect score is a curve which goes to 1. On the diagonal here represents the climatology. So the skill of the models to predict this 2-meter temperature has been assessed. So over a period of 10 years of real-time forecast, showing that the model are generally at week 2, at least have some skill to predict those 2-meter temperature, probability of 2-meter temperature in upper decile, larger than persistent, which is a blue curve. And this is for the lower decile, so for cold events, extreme cold events, where the model seems also to have some skill at this time range. Another approach is to use extreme forecast indices, which is quite popular in medium range forecasting, but can be extended to weekly means. So here we look at a cumulative distribution function of an event over an area. So here we look at 2-meter temperature CDF. The dotted line represents the climatology, and the solid line represents the forecast at different lead times, week 1, 2, 3, and 4. And this was for a specific extreme event. So large shift of the CDF are an indication of an extreme event. And the index is based on the integral between those two lines, between the climatology CDF and the forecast CDF, with a strong weight towards the tail of the distribution. And in this specific event, we see that the model predicted fairly well. The black line, by the way, is observed value. Predicted fairly well quite a large shift of high probability of an extreme event. For week 3, it's more modest. The observed anomaly is outside, mostly outside of the distribution. And for week 4 is very close to climatology. So this allows us to create those maps which was adapted here for the S2S models, for onset, ECMWF, for instance, showing regions of high probabilities for 2-meter temperature of EFI for 2-meter temperature, the regions where there's a risk of an extreme 2-meter temperature weekly anomaly. That was for week 2 in this case. So this allows us also to verify the skill of the system, and this was here preliminary results based on the ECMWF models. This is a skill from week 1 to week 4.5. So this is a Roth area once again. So climatology is 0.5. So if we are above 0.5, means that the model is better than climatology. And showing that actually even up to week 4, the model seems to have some skill actually. Although the skill is fairly low, but it's still better than climatology. It's also better than persistence to predict those events. So suggesting that those can be useful products for some applications. So I will now move to the second type of events with just one example of tropical cyclones, S2S prediction. Tropical cyclone here, as I mentioned earlier, the main reason we expect to be able to predict tropical cyclone activity is because the tropical cyclone activity can be strongly modulated by large-scale environment. We know for seasonal forecasting, the tropical cyclone, Atlantic tropical cyclone season is very strongly dependent on ENSO, on local SSTs. As a sub-seasonal, as the S2S time scale, one main source of predictability is the MGO. And this is here for, this represents anomaly of tropical cyclone activity over the southern hemisphere. When we have an MGO in phase 2-3, we tend to get more tropical cyclone activity over the Indian Ocean, and less over Australia basin and South Pacific. And as the MGO moves eastward, we can see that this activity is also moving eastward. So the top panel is in observations. Over the northern hemisphere, there is also a strong modulation of tropical cyclone activity by the MGO. A bit less over the Atlantic, I would say, than over the West Pacific and the East Pacific. So the other column represents this modulation of tropical cyclone activity by the MGO within the different models. And what we can see is that the model represents remarkably well this link between MGO and tropical cyclone activity. So all the models predict more tropical cyclone activity when we have an MGO in phase 2-3, and the opposite when we have an MGO in phase 6-7 over the Indian Ocean, for instance. So So if we add to that the fact that the models have some skill to predict the MGO, here this plot shows the predictive skill of the S2S models to predict the MGO. We can see that most of the models have some skill to predict the MGO. So we reach a correction of 0.5 around day 20, between day 20 and 25. On one of the models, the ECMWF model actually has some skill to predict the MGO beyond 30 days. So if the model has some skill to predict the MGO more than 30 days in advance, and we know that the MGO has, and they are able to represent the impact of the MGO on tropical cyclone, this suggests that the model should have some skill to predict some weekly anomalies or tropical cyclone activities, at least a few weeks in advance. So to check this, there's been a paper recently by Lee et al. So they evaluated the tropical cyclone activity in those S2S models. First, this paper looked at the ability of the model to represent the seasonal cycle of tropical cyclone activity for all the different ocean basins, showing that overall the model represents fairly well the seasonal cycle over the Atlantic. The bimodal the cycle over the Indian Ocean, North Indian Ocean, and also the seasonal cycle over the Southern Hemisphere basins. And then they assess the skill of the model to predict tropical cyclones at the sub-seasonal time scale from week 1 to week 4. And this panel shows a BRAS skill score, so computed over reforecast from 6 S2S models. And so that's the BRAS skill score for week 1 to week 4 for all the various ocean basins. And here the BRAS skill score well depends a lot on what is your reference climate. So the dotted line represents the BRAS skill score is your reference climate is a fixed climatology. So in which case we can see that the skill vary a lot from basin to basin. And also from models to models. Usually the ECMWF model has usually higher skills than others for tropical cyclones. And for some basin, actually, like Eastern Pacific, we can find some skill up to week 4, so which sounds quite good. However, if we change the reference climate to a seasonal varying climate, which is a solid line, then the score dropped. And here we can see that model has some skill in some basins up to week 2, sometimes up to week 3, but not beyond 3 weeks. And this is also represented here on the map of BRAS skill score for the ECMWF model, showing some skill here at for week 2, day 8 to 14, over all basically the basins. If we take, however, the seasonal varying climatology, we can see that there's not much skill over Atlantic. There's a little bit of skill over East Pacific on the Southern Hemisphere. So this means that in most cases, the skill we get in the left is mostly due to the fact that the model are able to reproduce the seasonal cycle. However, those forecasts were not bias corrected. So here the verification was performed just on the raw output of the model. Then this paper, they did a second set of assessment where they bias corrected the model, the raw output of the model using the other years of the reforecast. And here we can get much increase in forecast skill, even if we use the seasonal varying climatology and we get some skill over all the ocean basins, except mostly over the Atlantic, which is not surprising because at this time scale, that's a basin which is less affected by the MGO than the other basin. And that's a bit of contradiction with seasonal forecasting, which is Atlantic is one of the most predictable basin in seasonal time scale, but as a sub-seasonal time scale is probably one of the most difficult. Okay, and so the ability of, if the model has some skills to predict tropical cyclones, this can lead to some quite interesting products, like strike probability maps for a weekly mean. This is a week 3 strike probability maps for forecast starting in January 2011, for instance, when there was this very strong storm, Yazi. And this can be integrated in a sort of a multi-time range framework where seasonal forecasting can be used to warn for heavy seasons, like was the case here. The model, there was a La Niña season, so the model predicted a heavy season over the Australian basin, but without much indication of where this will happen. Then we have the standard range, which would be the set with a high probability of tropical storm hitting Australia, and then GO, which is a medium range where people can take action. Okay, I have 5 minutes. So I will go now to let's spend the last minutes to talk a bit about what are the current main problems with S2S prediction. So one of the main issues is a prediction. There's been a lot of progress in the prediction of sources of predictability. The prediction of the MGO in S2S models has really improved massively over the last 10, 15 years, but there are still some issues. One main issue is that the model, MGO in model is generally too slow and too weak. And the ensemble forecasts are also overly confident, usually. So the ensemble spread is usually too small compared to the IMS error. Another issue is the fact that the MGO has problems crossing the maritime continent. And this plot represents the percentage of MGO events which die crossing the maritime continent, which happen in real world, but in a small number of them. But in the model, there is more than double of them. Double of MGO are dying while crossing the maritime continent. So this is quite an issue for the prediction of S2S prediction over Europe, where a lot of predictability comes from the MGO. But if there is some point to predict the MGO, there is a major problem in the prediction of to predict the tail connections and of the MGO. So here we are looking at the Z500 anomalies, 3 pentats after an MGO in phase 3, which in our interim is characterized by a very strong positive NOC node. So that's well known. About 10 to 15 days after an MGO, you tend to get positive NEO. Well, you have more chance to get positive NEO. And that's in the different models, which have been classified by the resolution, from the lowest resolution 1 to the highest resolution 1. And we can see that the model do a good job in reproducing the patterns. So most of the models are going towards a higher probability of NEO following an MGO in phase 3. But the main problem is the amplitude, which is much, much underestimated by the model. So this means that the impact of the MGO on the weather over Europe is largely underestimated in our models. And this will affect, of course, the prediction of extreme events. This is from a recent paper from Stan et al., where they look more in details into those teleconnections in the various S2S models. On the first phase 7, here they look at 2 meter temperature, composite of 2 meter temperature anomalies, 11 to 15 days after an MGO in phase 7. So the right, top left is in the ERA interim, which show very strong wave train, which affect Europe. And the models are a bit all over the place in this case. What is interesting is that actually the model which seems to have the closest to ERA interim are GMA and Environment Canada, which are actually the model which are uncoupled. And we know that the coupling really helps to improve the prediction of the MGO, but it adds some errors, particularly in the western boundary occurrence, like the Gulf Stream, which affects the pathway of the tail connections. So, so it seems that if you want, that the coupling is usually can be quite damaging for the representation of those tail connections. For the SSW, the ability of the model to predict the SSW on their tail connection was assessed in a recent paper by Madden et al. 2019. They look at different types of vortex events. In general, they found that the predictive skill doesn't exceed 10 days for those events. But the tail connections in the 30 days following those SSW events, which is for the weak vortex event on top and strong vortex events in the bottom. Left is ERA interim, right is a multimodal for week 3, is relatively well reproduced by the model. Now, the patterns are remarkably well reproduced, but once again, the intensity is underestimated. So this will probably have an impact on the ability of the model to reproduce those cold waves over Europe in winter, following an SSW. So there's still some issue with the models, but good news is that the models are generally improving. We know that in medium range, there has been a gain of about 1 day of predictive skill per decade. For seasonal forecasting, there has not been clear improvement. There's been some improvement in the prediction of ENSO, but not much in the extratropics. So the question was, what about the S2S timescale? Has the model improved? For the MGO, there has been some very large improvement over the last 20 years. In the early 2000s, the ECMWF model didn't have skill to predict the MGO more than 2 weeks in advance. Now the model has some skill to predict the MGO up to 32 days in advance. So that has been quite a massive improvement in such a short period of time, 20-year period of time. But what is quite nice to see is that the forecast skill over in the high latitudes has also improved. Here we look at the skill of the model to predict 2-meter temperature over the northern hemisphere, which has significantly improved since 2006. And we have the same improvement for precipitation. Yeah, so I almost finished. Just to mention that another source of improvement could be the use of AI ML, so artificial intelligence machine learning methods. And to evaluate that, the S2S project organized a competition, a challenge last year. The goal was to provide the best forecast as possible of 2-meter temperature and precipitation for week 3+4 and 5+6 globally for the year 2020. And on this competition, the competitors were provided those S2S models. So the idea was to see if AI/ML method could provide a better calibration of the model on post-processing. But this competition was also open to AI/ML methods that to purely empirical methods that could replace dynamical models. So we had 49 participants. Only 5 of them succeeded in beating the benchmark, which was which is on the right, which was the ECMWF forecast after bias correction. On the right panel represents shows the scores for the top 3 entries for week 3+4, 5+6, 2-meter temperature and precipitation, showing that overall they provided quite some improvement from the ECMWF model, but the improvement was not that large. So this is just the first step. There may be a follow-up to this competition. The winning entry use interestingly AI/ML method, use multimodal ensembling, and it used AI/ML method to CNN methods to bias correct the model to provide a better calibration of models, but also to provide to compute the optimal weights of the multimodal ensemble. So they use AI/ML method in 2 ways. So what was interesting is actually the winning entries had very, very different use of AI/ML methods. And another question is are the S2S forecasts good enough right now for the use of applications? So this is not something the S2S project has done too much, but in S2S phase 2, we organized S2S real-time pilot initiative, where we provided the S2S data, which I mentioned earlier is 3 weeks in real time. We provide it in real time to 16 applications, and for a limited period of time, so which stops in November 2022, so very soon. So there will be actually, we will have a workshop in November where there is a planned workshop from 14 to 18 November 2020 to discuss those results. So I think I will just, this is an example from the disaster risk prediction in Southeast Asia, where they use S2S forecast to estimate the skill and to issue forecast to the AHA, which is a disaster risk agency in this area. Okay, on just the last slide, just to mention the future directions of models. There is different direction of models. Some models can go towards higher resolutions. Some go to more complexity, some goes to a larger ensemble size. So in the S2S community, yes, different centers have different strategies. Some like NASA goes to more complexity with aerosols, dynamical interactive aerosol in their models. Some go to very high resolution oceanic model. At ECMWF, in our next system, in the 48-hour cycle, we found that actually increasing the resolution didn't really help the prediction at this S2S time range. It made the extreme events more realistic, more realistic tropical storms, but in terms of predictive skill, it didn't really have. So we will go instead to double the ensemble size on the frequency, which will be beneficial actually. Which is increased ensemble size should be beneficial for the prediction of extreme events by producing a more accurate tale of by having a more accurate representation of the tail of the distribution. Okay, I think I will stop here with the conclusion. And I think I let people read it. And I think we can go to the questions.
Thank you very much for this illuminating talk. So we have some time for questions now. Well, I can start, but Holger, please.
In the second part of the talk, you made the remark that certain forecast skill of the model is still far away from the intrinsic predictability, which means you have a certain expectation how well the phenomenon is predictable. So what's your general feeling about these S2S predictions? How far could one?
Well, that's a good question, a very good question. If I can go back to the talk. Yeah, in one of the slides, I didn't go too much into it, but yes, I mean, the interest in predictability of the model, it's difficult to fully assess. I mean, one method people use is to use one ensemble member. You can use one ensemble member as a truth, and then you try to verify this. And there was one example here from, didn't go through it, from the MGO prediction, which shows that in gray was this implicit, that's in this paper by Nina et al., where the black line shows, so this shows the predictability from the models, that's the black line. That's the gray line. The gray line represents this interest in predictability versus the actual predictability, showing that there is still a lot of large room for model improvement in that regards. The problem is that this type of estimation often overestimates the intrinsic predictability, depends on the model ensemble is generated. It can also underestimate it if the model doesn't have the right processes. For example, if the MGO is not able to represent MGO connections over Europe, then the potential predictability will be very low in the model because it doesn't have this process. So it's an interesting question, but we don't know, I think, currently what is the truth to level of predictability a model can achieve if it was perfect.
Thank you. Yes.
Okay, thank you very much for your very interesting presentation. I have interested to know, how do you apply this when you have spoken about the prediction of a statistic of small scale events like flash floods? You know, flash floods in Mediterranean.
Yeah, no, I put a flash flood there. I haven't seen any example exactly of flash floods. There has been some tornadoes, for example, in the US, which can be strongly modulated by the MGO. For flash flood, I would imagine that it can be, if it comes from large scale events, if it can be modulated by some large scale events, then there should be some predictability. But yeah, that has to be checked. Yeah. But once again, I mean, it's a risk over a large period of time on the large area. Yeah.
Hi, thanks for your very interesting talk too. If I understood correctly, you said that one of the main limitations for advancing the forecast is a good understanding of teleconnections of, for example, MSHOT, the Madden Julian Oscillation with other. So is there any strategy on your project to improve this determination or quantification or assessment of these teleconnections?
Yes, there has been quite a lot of work ongoing to try to address, to understand it. One first hypothesis, it comes from the errors in the representation of the MGO itself. We know the MGO is too weak in the models, so that may also affect the amplitude of the connections. However, if we do an experiment where we roll out the tropics, where we have a perfect tropics, we find slightly better connections, but still way too weak compared to, which suggests that the error comes from the higher latitudes. So one hypothesis is biases in the subtropical jet stream, which is a very important pathway for those Rossby waves. And the models, S2S models, tend to move this subtropical jet too much to the west. That's not fully understood why. But yeah, that's where I think we are. So the model have a tendency to go too much towards sort of La Nina conditions, if you want. And we have seen that during La Nina conditions, the tail connections are much weaker than during El Nino conditions. So it's linked to some systematic errors in the models in the higher latitudes. So can that be held by a higher resolution model? That's maybe not. Or is it so some error, some problem in the coupling? I mean, we know there's a lot of errors also in the ocean atmosphere representations. So I would say that's an active phase of an active area of research.
Question. Time for 2 more quick questions, please.
Okay. Yeah. Thank you for your presentation. And I have a quick 2 questions. And the first one is, I remember seeing that the S2S participating models, many of them have an atmosphere-ocean coupling, but a few of them do not have a LC coupling. So I'm wondering if I remember correctly, but how those models which does not have an atmosphere-ocean coupling produce forecast. And the second question is, there was a 3 weeks heat wave prediction, which was very good over the United States. Yeah. So is there any discussion in the paper why the heat wave prediction was successful at 3 weeks ahead?
Okay. So to answer your first question, which is about the non-coupled models. Well, for this time range, I mean, of course, if you look at seasonal forecasting, you need to be coupled. For the S2S, for this time range, I would say that those uncoupled model at GMA and ECC, that's the old model of ECC, now they are coupled. But they used to be, they were not the worst in terms of skill scores globally. For the MGO, which for the Madden Oscillation, however, they tended to have a lower skill than the other model on average. But overall, if we look at the skill over US, over high latitudes, I would say it was relatively comparable to others. So you can do successful S2S forecasts even with a model with persistent SSTs. With the coupling, you introduce better, you get better MGO. We know that, usually better skill in the tropics. But it's not, so the ocean atmosphere coupling is not a necessary condition, if you want, for the forecast at this time range. The second question is if we understand why the model was successful over Russia at this long lead time. Well, the quick answer is we don't really know exactly why. I mean, the model was pretty good at predicting the weather regimes, the blocking for such a long time over this region. It could come from the soil initial conditions. I don't know. We were not. It's still an open question.
I'm sure we have many more questions for him, but we have to move on. So let's thank him again.